Chapter 9, Rotational Motion. This lecture will help you understand angular acceleration, conservation of angular momentum, and centripetal force. Linear acceleration in meters per second squared is the rate of change of linear velocity. Likewise, the angular acceleration in radians per second squared is the rate of change of angular velocity. There is a complete correspondence between the equations for angular motion and linear motion. Study this chart carefully and become familiar with the two sets of equations. When we studied linear acceleration, we saw this figure. The car is speeding up with a constant acceleration and moving to the right. The acceleration is positive. The direction of the acceleration is in the same direction as the motion. In this motion diagram, the car is slowing down with a constant acceleration of 10 meters per second squared. The acceleration in this case is negative, which is commonly called deceleration. When an object is slowing down, the direction of the acceleration is opposite the direction of the motion. In angular acceleration, we have similar situations. In the top left figure, the wheel is turning counterclockwise, the positive direction. The wheel is speeding up. The angular acceleration is in the direction of motion and is also positive. In the top right, the wheel is turning clockwise, negative. The wheel is slowing down, so the angular acceleration is opposite the direction of motion and is again positive. In the lower left, the wheel is spinning counterclockwise and slowing down, so the angular acceleration is negative, opposite the direction of motion. The lower right figure, the wheel is spinning clockwise and speeding up, and so has a negative angular acceleration. A rotating pulley, 24 centimeters in diameter, is rotating at an initial angular speed of 30.5 radians per second. The speed is steadily increased to 41.5 radians per second within 6.30 seconds. Find the pulley's angular acceleration and find the final linear speed of a point on its rim. For part A, we need the angular displacement given the angular acceleration and time interval. The working equation solves the basic equation for the angular acceleration. We know the initial and final angular speeds and the time period. This allows us to find the angular acceleration as 1.75 radians per second squared. For part B, we need to find the linear speed given the angular speed and the radius. Since we know both of these values, we find the final linear speed of 4.98 meters per second. As we did with angular velocity, we can relate angular acceleration to tangential acceleration. The tangential acceleration is the rate of change of the tangential velocity, which is the rate of change of omega times r. Since the radius is constant, it does not change. So the tangential acceleration is the radius of the circle times the angular acceleration, alpha. According to Newton's second law, an unbalanced or net force will cause a mass to accelerate. We also learned that a torque is the tendency to produce change in rotational motion. Torque depends upon the amount of force applied and how far the point of rotation is from the force. Torque is the force applied at the distance from the axis of rotation. In circular motion, the distance from the axis of rotation is the radius of the circle. The force is the mass times the tangential acceleration. The tangential acceleration is the angular acceleration times the radius, which we write as the angular acceleration times the mass times the radius squared. We can write down the torque for each particle as tau sub 1 equals m sub 1 times r sub 1 squared times the angular acceleration. Tau sub 2 equals m sub 2 times r sub 2 squared times the angular acceleration. Tau sub 3 equals m sub 3 times r sub 3 squared times the angular acceleration. The net torque is the sum of all the individual torques. Since the angular acceleration is the same for all the individual particles, we factor it out and end up with a large sum of mass times radius squared. The large sum in parentheses, we give the name moment of inertia and give it the symbol I. In symbolic notation, we write alpha times the sum of all the individual masses times the distance from the axis of rotation squared. The big thing that looks like an E is the Greek letter sigma and means sum all the values. The moment of inertia is defined as the sum of the masses times their distance from the axis of rotation squared. The units of moment of inertia are kilograms, meters squared. A very important point is that the moment of inertia depends on the axis of rotation. If we change the axis of rotation, we change the moment of inertia. Using this definition of moment of inertia, Newton's second law can be stated in terms of rotation. A net torque will cause an object to experience an angular acceleration, where I is the moment of inertia. The moment of inertia is the rotational equivalent of mass. An object's moment of inertia depends not only on the object's mass, but also on how the mass is distributed around the rotation axis. If the mass is concentrated around the rim, as in figure A, the larger moment of inertia means the merry-go-round is harder to get rotating. In B, all the mass is concentrated at the center, and it has a smaller moment of inertia, and it's easier to get the merry-go-round rotating. Even though the two cylinders are of equal mass and radius, the hollow cylinder has more rotational inertia because its mass is concentrated farther from the axis of rotation. In earlier chapters, we defined the momentum as the mass times the velocity of a particle. A body in linear motion has the property of inertia, which keeps it in a state of linear motion unless acted upon by an unbalanced force. A rotating body has the property of rotational inertia, or moment of inertia, which keeps the body rotating until acted upon by an unbalanced torque. The spinning skater must have angular momentum. The angular momentum for a rotating body is defined as the moment of inertia times the angular velocity. Comparing linear and rotational motion, we get the two sets of equations, the force and torque equations, the linear and angular momentum equations, and the equations of impulse written in terms of linear and angular motion. The angular momentum of a system remains unchanged unless acted upon by an external torque. In the two cases, the skater is spinning with the same angular momentum. In A, there is a mass at a large distance from the axis of rotation, and the skater spins more slowly. In B, the mass is concentrated near the axis of rotation. She pulled her arms in. her rate of spin is much higher. To slow down, all she needs to do is extend her arms. Why does a roller coaster stay on a track upside down on a loop? The answer is centripetal force. We usually think of acceleration as a change in speed. Because velocity includes both speed and direction, acceleration can also be a change in the direction of motion. Any force that causes an object to move in a circle is called a centripetal force. A centripetal force is always perpendicular to an object's motion and toward the center of the circle. On the left, the rock on the end of the string is kept in circular motion by the tension in the string. On the right, the car makes the curve because of friction of the tires. In both cases, the force is directed towards the center of the circle. This is centripetal force. A particle of mass m moving at constant speed v around a circle of radius r must always have a net force of magnitude m v squared divided by r pointing toward the center of the circle. This is not a new kind of force. The net force is due to one or more of our familiar forces, such as tension, friction, or the normal force. Centripetal force is defined to be the mass rotating times its linear speed, which we also call tangential speed, squared divided by the distance from the axis of rotation, or the radius. Since force is a vector, the direction of the force is always towards the center of the circle. Centripetal means center seeking. A 50-kilogram passenger on an amusement park ride stands with his back against the wall of a cylindrical room with a radius of 3 meters. What is the centripetal force of the wall pressing into his back when the room spins and he is moving at 3 meters per second? You are asked to find the centripetal force. You are given the radius, mass, and linear speed. The formula that applies is F equals mv squared divided by r. Solving gives us a centripetal force of 150 newtons, directed toward the center of the room. The force that causes this centripetal force is actually the normal force of his back on the wall. Acceleration is the rate at which an object's velocity changes as the result of a force. Centripetal acceleration is the acceleration of an object moving in a circle due to the centripetal force. Centripetal acceleration is the speed squared divided by the radius of the path. The units are meters per second squared. A motorcycle drives around a bend with a 50-meter radius at 10 meters per second. Find the motorcycle's centripetal acceleration and compare it with g, the acceleration of gravity. You are asked for the centripetal acceleration and a comparison with g, which is 9.8 meters per second squared. You are given the linear speed and radius of the motion. The centripetal acceleration is v squared divided by r. Substituting our known quantities, we get a centripetal acceleration of 2 meters per second squared. The centripetal acceleration is about 20% or 1/5 that of gravity. In Chapter 7, we define work done as equal to the amount of force times the distance moved in the direction in which the force acts. Power is a measure of how fast work is done. It is the time rate of change of the work. The units of power are watts or horsepower. In a rotational system, the power is the torque times the angular velocity. How many watts, where 1 watt is 1 joule per second, of power are developed by a mechanic tightening bolts using 50 Newton meters of torque at a rate of 2.5 radians per second. How many kilowatts? Since the power is the torque times the angular velocity, both of which are known, the power is 125 Newton meter per second, or 125 watts. Since 1 kilowatt is 1,000 watts, the power in kilowatts is 0.125 kilowatts. What horsepower is developed by a racing engine with a torque of 545 foot-pounds at 6,500 RPM? Since we are given the angular speed in terms of RPM, we must convert to radians per second and get 680 radians per second. The torque and angular speed are known, so the power is 37,600 foot-pounds per second. Since 1 horsepower is 550 foot-pounds per second, the total power is 674 horsepower.